Hi class, and welcome to lesson 2. Today we're going to talk about sets. We only define sets informally, and we just define them as a collection of things, but we can write them down formally mathematically. So for example, if we want to write down the set of whole numbers from 1 to 4, we write down the numbers 1, 2, 3, and 4 in between two curly braces, with commas between the elements. Another handy way to write a set down, which we will discuss a little bit more later, is to write down the type of elements and then a colon and the rule that the element satisfies. So this funny looking E and this funny looking Z will be discussed shortly. But this is another way to write down the set of elements 1, 2, 3, and 4. So that funny looking E is actually what's called the membership symbol. It's used to denote whether or not an element is in a set. So if we let A be the set 1, 2, 3, and 4, then 2 is a member of A. And we say this in a lot of ways. We might say 2 is in A, 2 belongs to A, 2 is a member of A, 2 is an element of A. But they all mean the same thing. It just means that 2 is one of the elements that's in the set A. And if we want to say some element is not in the set, we put a slash through the membership symbol. So, for example, 0 does not belong to A, or 0 is not an element of A. Let B be the set 2, 4. Then every element of B is also in A, because 2 and 4 are in A. A mathematically precise way to say that, or a logically precise way to say that, is if X is in B, then X is in A. And what this means is that B is a subset, or B is contained inside of A. So this is a subset of a set. And you write this with this little contained in symbol. So B is contained in A. And likewise, we can put a slash when one set's not contained in another one. So A is not contained in B. For example, 1 is an element of A, but 1 is not an element of B. So A is not contained inside of B. We say two sets are equal if they have the same elements. So if A is the set 1, 2, 3, and B is also the set 1, 2, 3, then we say that A equals B. Another property of equality is double containment. So if A is contained in B and B is contained in A, then A and B are equal, and vice versa. So every element of A is also in B, and every element of B is also in A. Then they must be the same elements, and therefore they're equal. Whereas vice versa, if they're equal, then all the elements of A are also elements of B, and all the elements of B are also elements of A. We can add operations onto sets. So if A and B are sets, the union of A and B, written A with a little cup symbol between the A and the B, is the set of all elements in A or in B. So remember, in mathematics, the OR is always inclusive OR by default. That means the elements can be elements of A or B or both. So for example, if A is the set 1, 2, 3, 4, and B is the set 2, 4, 6, then A union B is 1, 2, 3, 4, 6. So that includes all elements of A or B or both, but we don't count multiplicities. So 2 is an element of A and of B. That makes 2 an element of A union B, but it's not counted twice. That's because the membership is a binary operation. We just want to know if 2 is in the set or if it's not in the set. And it is in the set, so we list it. But you don't list it 2 times because it can't be in something twice. It's just in it. A similar operation is the intersection. So here we write A cap B, a little cap sign in between, represents the intersection of two sets, and it's all the elements that are in A and in B. So in this example, where A is 1, 2, 3, and 4, and B is the set 2, 4, and 6, then everything in A and in B is just 2 and 4. So that's where the two sets intersect one another. Usually we're interested in a particular kind of set, and we call this the universal set. Or, in probability, it'll often be called the sample space, and we'll represent it with this capital omega symbol. So, for example, if I'm rolling a die, the universal set would be 1, 2, 3, 4, 5, and 6. When I roll a die, I'm not worried about rolling a car or rolling a chair or something. I'm going to get a number, 1, 2, 3, 4, 5, or 6. I'm not even going to get a number like 2.7 or negative 13. So the universal set are the set of things that we're actually interested in. And it's the set of all things that we're interested in, so we have to make sure not to leave out anything. But we don't want to include crazy things. So subsets of the universal set are going to represent what we call events in probability. So for example, if we want to roll a 5 or higher, we represent that with a set. And it's the set of outcomes 5 and 6. The complement of a set is everything in the universal space that's not in the set. So we denote this with an A with a super C, or whatever the set's called, with a super C. For example, if we fail to roll a 5 or higher, that's the complement of A, meaning we didn't roll a 5 or higher, which would be everything else, 1, 2, 3, and 4. That's not inside of A. There's some common universes. One is the natural numbers, which is also known as the counting numbers, 1, 2, 3, 4, 5, 6, 7, and so on. The integers is 0, plus and minus 1, plus and minus 2, plus and minus 3. So we're building up here. If we take the natural numbers, the usual counting numbers, and add in 0, as well as the negatives, we get what we call the integers. And then we could actually take fractions between them, so we call that the rationals. And we denote that with a Q. That's the set of A over B, where A and B are integers, and B is not 0, so we don't divide by 0. And then the real numbers, if you want to see a formal definition of this, you should take real analysis. But for this class, we're just going to say it's all the numbers on a number line. So, for example, pi belongs to R, but pi is not a rational number. And similarly, root 2 is real, but root 2 is not a rational number. So there are real numbers that cannot be represented by a fraction of one whole number over another whole number. Another operation we can perform between two sets to form a new set is called a cross product. So let A and B be sets. The cross product is all ordered pairs, A comma B, where A belongs to the set A and B belongs to the set B. For example, if the set A is the set little ABC, and the set B is the set 1, 2, then their cross product gives us the pairs of A1, A2, B1, B2, and C1 and C2. So it's just pairs of elements from A and B. Finally, you also want to know what the power set is. The power set of A is all subsets of A. In fact, it's a set of sets. So it is a set itself, but it contains sets as its elements. So the power set of A is the collection of all B, such that B is a subset of A. For example, let A equal little ABC, then the power set of A would include the sets of the set A, for example, of little a, because that set is a subset of the set capital A. It would have the set A comma B, and it would even have the set A comma B comma C, as well as that first set, which looks like a 0 with a slash through it. Remember that that's what we use to represent the empty set, or the set that has no elements in it. So it's a set that's just empty. You have to be a little cautious here. So B, little b, is not an element of the power set, because little b is not a subset of the set A. It's an element of the set A, but not a subset. But the set containing little b is an element of the power set of A, because the set containing little b is a subset of A, so it satisfies the rule. That's all there is in this review of sets. So if you have questions, please stop by and ask. And remember, this is a prerequisite for the course, so hopefully this will serve as a nice refresher. All right, talk to you next time.